Hello students. The lab 8 and 9 involves a 5-step process. The first one, as it's stated, it's the generation of the netlist of all the cells from the virtuoso. The second step is the characterization of the standard cells and the generation of .lib and .wav file from the Liberate tool. The third step is to compile, elaborate and simulate our RTL code, and the fourth one is to synthesize our RTL code with constraint and the model file that we have generated from the Liberate tool. And the fifth one is to do the same step that we have done in step number 3, that is compile, elaborate and simulate, but this time it is being used using synthesis code. So step number 1 is nothing but the generation of netlist of all the standard cells. So this particular step have 3 steps involved in it. The very first thing is to create a schematic. So this schematic, I have named it as standard lib, std lib, and I have pasted all my symbols of the cells that I have designed. So here I have an inverter, a 2-input NAND, 3-input NAND, 2 and 3 input NOR gates, as well as a D flip-flop without set and reset, and a flip-flop with set and reset. Note that these cells were not connected, so all are unconnected, and just click on this check and save. You will end up with some warning. It's just okay. You just click close and then launch your ADEL window. So click on launch ADEL, and this will bring the analog design environmental tool. Now there are 2 steps that are involved. The first step is to define your environment. So click on setup, click on environment, and here at the very beginning of your environment switch wavelist, we have to define AV underscore extracted and then a space. So this particular process would actually help the AD or the Spectre simulator to pick your AV extracted view to the symbol that I have attached. So just click OK, and next is the generation of the netlist, which could be done by clicking on the simulation and then click on netlist and click on create. So when I click on create, this will actually generate a file which is named as input.acs, and here you could able to clearly see that there are syntaxes like VDD, which has been appended with VDD with exclamatory symbols, which is nothing but the global symbols. Okay, so this is the AV extracted cell view, which has capacitance and the resistance of all the poly and metals that we have attached, and also it has the PMOS and NMOS transistors and their interconnections. So now click on file and click on save as, and save this particular file as dut.ses, and then click save. Since our Liberate tool doesn't understand the syntaxes with exclamatory symbols, we need to run a Perl script which will try to remove this exclamatory symbols out of this netlist. So right now I'm in the home directory, and here I have pasted my DUT file under the name dut20.ses. So this is a file that I have copied into the home directory. Now in order to work further, it would be a better practice to create your directory under the name of you, so that it will be easy for you to distinguish from the other users. So I'm just going to create a directory which is known as sample, and then I'm just going to get into the sample directory, and then again you need to create 2 directories, one to run your Liberate tool and the other one to run your synthesis codes. So I'm just going to create a directory Liberate, and later I'll be creating one more directory which is synthesis. So now I'm just going to get into this Liberate, and my present working directory would be this. Now I need to copy the DUT 20.scs into this particular folder, and also the other file, which is the script file, which is available under the directory SPTR. So I'll just get into this home directory and then the script directory to show you what is there in it. So here you could be able to see there are two files. One is sptr to elc.pl, so which is the Perl script which will try to remove the exclamatory symbols out of the netlist. The other one is the tickle file that is meant to be used during our Liberate tool. So I need both these files to be copied, so I just give the copy command with start, which will select both the script files, and then I'm going to paste it into my working directory sample and then Liberate. So this would copy all of these scripts into my Liberate directory. So now I also need my DUT file to be copied into this, so for which I just give this command and then I just copy even that. So I have all these files. Now that I need to run the Perl script by typing the command Perl sptr to elc and the dut.scs. So when I run this command, the command has removed all of these exclamatory symbols from this particular directory, which if you want, you can just visually see it by opening any of the editors. So before we run the Liberate 2, we'll just get into the file, the tickle file, and we'll just look into it what exactly this script is all about. So there are basically three templates that are being defined. The first template is basically defines the delay template, and the name of the template is given delay underscore 3x3, and here there are two indices that are being given. The first index is nothing but the input sleeve, and the second index value is nothing but the load. Now here the values that are being placed inside this index 1 as well as index 2 are basically the normalized value, where the normalized value will fall between the value of 0 and 1. Now similarly, I need to define a template for the power computation, and I have given the name of the template to be power underscore 3x3, and the last template is nothing but the constraint template, which again has two index values, and I've given the name constraint underscore 3x3. Note here the index 1 and the index 2 value will be same, and basically this constraint index is meant to characterize the setup time, hold time, minimum pulse width, and basically in general it is meant for characterizing the sequential cells. The second thing that I have to do is to define the operating condition, so which is being defined through the set underscore operating condition. And since we are working with 180 nanometer technology, I have defined the voltage to be at 1.8, and this is going to be a typical process, so I'm going to define the temperature to be 25. Followed by this particular step, we have to read in the spice netlist file as well as the model file. So in order to read this particular model file, we have to define this particular variable, which is set var, and the variable that I'm going to define is external simulator model include, and this particular variable defines the path where I have kept this gpdk.scs. And next comes this out of the leaf definition. So this is basically a map between the pin position of my NMOS and PMOS to the model file that I have. So here the letter or the number 0 denotes the drain, and 1 denotes the gate, the 2 denotes the source, and 3 denotes the body. So these pin positions would get mapped to our model file, which I can show it here. So here this NMOS 1, which is from my model library, I could able to see it requires 4 inputs, and these 4 inputs are being defined through this pin positions in my define leaf definition. So once this is done, the next thing is to read my netlist file. Since the read spice command will look for the spice netlist file, and we have generated the netlist in terms of spectre format, I have to provide the switch, which is nothing but hyphen format followed by the spectre. So this will intimate to the tool that the file that is being read is in spectre format. The next comes the definition of rows of pins that I have defined in my cells, and the application of all this delay, power and constraint templates to the cells that I have created. Since all of the combinational logic cells have the pins which is defined with letters A, B, C, those combinational cell pins are being defined here. The letter D actually pin name that I have given for the D flip-flop, which I have included here. And for all the combo logic, I have given the output pin name to be Y, which has been defined here, and the QN or basically I have defined for the output of my sequential circuits. The next comes the clock, which is again this is with respect to the sequential block, and the asynchronous signals are defined using the switch async, and then later the next three set of statements is nothing but the templates that we have defined earlier is being applied to all to the cells that I have defined at the bottom. So this includes the D flip-flop with set and reset, the D flip-flop without set and reset, the inverter, NAND and NOR. Next comes the actual process of performing a characterization. So this is done by invoking the command char underscore library, and basically there are three different models that are there, but we are going to use this ECSM model in order to characterize all the cells. And once the characterization is done, we are trying to read out the .lib file using this write underscore library and then followed by a name with .lib extension. And we are also generating the HTML files using the statement that is defined under write underscore datasheets with format as HTML and the directory name and the switch as dir and the directory name tthl, and the type of process that we are using is a typical. Now once all of these things have been written out, the next thing is to generate the .v file. Note here, you should not generate the .v file in the same run of character underscore lib. Yeah. So now it's time to run the Liberate tool. But one thing we have to yet to see is check whether we have copied all the model file that is required. So this list command doesn't show us any model file. So this model file have to be copied from the home directory where there is a folder named as models. So that model file will have gpdk.acs, nmos1.acs and pmos.acs. So I'm just going to copy all of these commands with the following command. So I'm just going to navigate to the home directory and then the models, and I copy all the files that are there in that models directory into the present directory. So now when I type the ls command, you could able to see that I've copied all the model files with .scs extensions. So these are the three files. So now I can just invoke the tool Liberate with the following command Liberate, and then the tickle command, the tickle file, and then I pipeline the logs through this command, and I give a name for the log to be saved. So just click on enter, and this will start characterizing your cells. So this has taken quite a long time to generate the .lib as well as the HTML file that we have given at the end of the tickle file. So now there is a status that is given. I have simulated 7 cells and all the 7 cells has got passed. So it's a requirement that everyone have to have this tickle file being passed. So now we'll just look into the file that is generated by typing this ls command, and that has to show us the lib file that has got generated as well as the folder tt_html directory that has created. Now to just give a glimpse of what it has generated, I'll just get with the directory tt_html, and then I'm just going to invoke the Firefox to open this index.html file. Yes, this is the output that was generated with index.html, and you will be able to see all the pin capacitance, leakage power, delay, and the constraint information like hold and setup time. So all the informations are available for each of the cells that we have characterized. I can even just get into the inverter and see those informations in it. Yes, now it is time to generate the .vlog file, one containing the timing information, the other one without the timing information. So first I need to invoke the Liberate tool by typing Liberate and then enter with the command read underscore library and the standard cell library with .lib extension. So this actually reads all the library cells into it, and now it's time to write out the Verilog file with the command write underscore Verilog and a name of Verilog file with .v extension. So I'm just going to give nd to denote that this Verilog file will not have any timing information, and this is the command that is used. And the other one is to have a Verilog file with timing information, for which I need to specify a switch spec param and then the table style, which will be in the form of min, average, max, and the name of the file that in which I just want to store the information. So this time I'm just going to end with d.v in order to denote that this contains the delay information. So that completes the job of generating the Verilog files. So you can just type the command exit to come out of this Liberate tool. Now it's time to perform the step 3 wherein we are going to create an RTL code and a test bench code, and then need to do 3 processes, namely the compilation, elaboration, and then simulation. So for which I need to first go to the directory under sample, create a directory with a name where you can keep all your HTML files over there. So I'm just going to create a directory synthesis, and now navigate to this directory. Since I've already created the Verilog files for a full header, I'm just going to copy those files into this particular folder. And now that I have copied all the files, which you can see it, so it has 2 design files. The topmost module is the fullheader.v, and the test bench, which has a name of fullheader_tv.v. So now I just need to invoke a tool in order to do the compilation, elaboration, as well as simulation, for which I need to type the command nc launch. So this is the window that appears after you invoke this nc launch command. Note, the directory is right now is not pointing to the directory where I have invoked the tool, and also there is one more cds.lib which is not again pointing to the directory where I have invoked the tool. So you need to first set the design directory to the current directory that you are working in. So click on File and then click on the Set Design Directory, and make sure that you are navigated to the directory, to the home, and then into the sample, and then into the synthesis, and then click OK. And right now just click on this create cds.lib file and go with the default option, click on save and click on OK and click OK here. So now this defines files that we had in our directory, and the other end we're able to see that the CDS file that right now we have created is present in our current directory. Now it is the time to compile each of the Verilog file that I have towards the left side. So just select the file and click on this vlog, which will launch the compiler, and then the test, and then the half adder. Okay. So all of these three files have been right now compiled. So when we compile, the compiled version will be available under this work lib. So here if you're able to see, these are the module name that we have given for the full adder, half adder, and for the test bench. Now next step is to elaborate it. So in this case you need to select the topmost module. In our case this will be the test_fa. So this is the module that calls the full adder, and inside the full adder we are calling the half adder. So now select the topmost module and then click on this elaborate radio button. So once the elaborate is done, you could be able to see that the snapshot is highlighting with a plus symbol. Just expand this particular option and you would get a work clip pointing to a test module name. So select this particular module and then click on the launch simulator icon. So this would actually invoke a tool, a simulator tool, wherein we have two windows. One is the console window, the other one is the design browser, and the third one is just, you can just close it off. So we are going to work with the design browser window. As it is shown here, the top module name of my test bench is highlighted here. So just select the module name and then select all the signals using the shift key. So I have selected all the signals of my full adder, and then once the selection is done, just click on this wave icon, which will actually copy all the signals that I have selected to a waveform window. So this actually launches the waveform window, and now click on this play button to run the simulation and just verify your waveforms. After verification, you can close all the windows that you have opened, including the NC Launch.